So in this video, we're going to talk about all the things that we should look for when we're making our sketches. So this is the curve sketching checklist. So I'm going to try and give a little bit of details about each thing in here so we can remind ourselves what we're looking for and how we find it. But we're going to put all these things together to sketch our graphs in the next few videos. So you might notice that there's quite a few things in this list. We're going to talk about what we need first. The first thing you should always look for is the domain. So we want to know, where is the function defined? Okay, so here we're looking for all allowable x values. Okay, so what you're going to want to think about, so your bad x's is normally the easier thing to find. So you don't want to have the denominator equaling 0. You don't want to have the square root of a negative. You don't want to have ln of, I'll write negative, but you can't do ln of 0 either. So you don't want anything less than or equal to 0 in here. So those are some common things to look for. I guess you also, for the trig functions, the ones with denominators, you don't want the denominator to equal 0. So for instance, for tan of x, you don't want to have cos of x equaling 0, because that's the denominator. And so there's other ones as well for those trig functions. So the domain is very important. It's something that we always want to think of, and we want to think of it first. Okay, now the next thing that you might want to think about are the x and y intercepts, if they exist. Okay, so x-intercept and the y-intercept. These are points we usually want to include in our sketches, assuming that they're sort of not too difficult. So if you want the x-intercept, you set y equals 0 and solve for x. Okay, if you want the y-intercept, you set x equals 0 and solve for y. Okay, so those are some important points we usually want to include. So now something that kind of goes with the domain is, for all the bad x values, you want to think what happens there. Okay, so you might have a vertical asymptote. Okay, so you want to know if there's vertical asymptotes, and the holes, if there's a hole in your graph. So these are x values, x values that are not in the domain. Okay, so how do I tell the difference? So this is going way back. If you get a vertical asymptote at, say, x equals c, then what's going to happen is your limit as you approach c of your function is going to go to plus or minus infinity. So it's going to get really, really big. Okay, so that's going to tell you that x equals c is a vertical asymptote. Okay, now there is one other, in fact, maybe I'm going to move this up a bit. Okay, so that means that x equals c is a vertical asymptote. You want to remember that the log of x, has a vertical asymptote as x approaches 0 from the right. Okay, so you can't ever plug in a negative value in a log, so that's why you have to approach from the right. But 0, there's a vertical asymptote there. Okay, so what you're really looking for Well, let's do the wholes first. So when do you get a whole? This is actually when the limit as you approach c of f of x is equal to some value k. Okay, but c is not in the domain. Okay, but the limit exists and equals some number. That's going to mean that you have a whole at the point ck. Okay, so how do you tell the difference without doing the limit? For these ones, for the wholes, you're going to have factors that cancel. Okay, so that's what makes the limit exist. Okay, and then to find the y value, what you're going to do is plug the x value into the simplified. Function, so after you cancel. Okay, then you can plug in the x value, that's going to find your y value. So for the vertical asymptotes, you're going to have your denominator is equal to 0, but your numerator is not equal to 0. Okay, or you're going to have the log. Log of x as x goes to 0. So those are sort of the main two. But when your numerator does not equal 0, it means that there's no canceling that can happen. So those are the main ones. Now you could have that they're both 0, but there's some canceling, but then the denominator is still 0 even after that canceling. Then you're going to get a vertical asymptote. Okay, so that's sort of what's going on there. So another thing we want to look for is horizontal asymptotes. Okay, so remember when we're looking for horizontal asymptotes, what we want to do is take the limit as x goes to infinity. So you want to know what happens as x is getting very large. Okay, if this equals some number, then your y equals k is a horizontal asymptote. Now you might remember the trick. So if you have a rational function, so that's a polynomial over a polynomial, then if your degree of the top equals the degree of the bottom, then you have a horizontal asymptote at y equals the leading coefficients. Okay, so that's the coefficient of the one on the top divided by the coefficient of the one on the bottom. And if your degree of your bottom is bigger than your degree of your top, then y equals 0 is a horizontal asymptote. And if the degree of the top is bigger, then you don't have a horizontal asymptote. Okay, so that's a trick you can do for rational functions, but really what you're doing is taking the limit as x goes to infinity. So remember, when we want to compute those, we just divide all the terms by the biggest power of x. Normally the biggest power of x in the denominator. Number 5, this is sort of the least important one, but can save you time if there is symmetry, but is to look for symmetry. Okay, so normally we look for even and odd. Okay, so if it's even, I guess I should have done this in green to match. But if it's even symmetry, you're going to have f of negative x equals f of x. And then it's going to be symmetric about the y-axis. Okay, and if it's odd, then you're going to have f of negative x is equal to negative f of x. And it's going to be symmetric about the origin. Okay. So if you're going to cut one, number 5 is the thing that you should cut. So number 6 and 7, so all of this so far is pre-calculus. Okay, we haven't really added anything new. We've just sort of revisited everything that you probably saw in a previous pre-calculus course. Number 6 and 7 is when calculus comes in. So things that we also want to include in our graphs are the critical points, okay, and intervals where the function is increasing and decreasing. So we want to make sure that those match. Okay, so how do we find those? Well, to find our critical points, we want to find our critical numbers. So these are x values where the derivative is 0 or where the derivative is undefined. Okay, so we want to take our derivative, find where it's positive and negative. Well, find where it's 0 and undefined. And then for increasing, this is when the derivative is positive. And for decreasing, this is when the derivative is negative. So that means that we're going to make our table. So find critical numbers, put on a number line to split the domain, and test a point in each interval to see if the derivative is positive or if the derivative is negative in that interval. So we want to know if it's positive or negative. That's how we tell where it's increasing and decreasing. So then we want to find the y values for our critical points because we want to plot all of these critical points. Okay, so this one is all about the first derivative. Okay, now for number 7, we're going to be looking at the second derivative. So we want to find all our inflection points. And we want to know where is it concave up or concave down. Okay, so inflection points, not all of these are going to be inflection points. So what we want to do is we want to find our possible inflection numbers. Okay, so that's when the second derivative is 0 or the second derivative does not exist. So we find all those numbers, and then we do the exact same thing we did before. So put possible inflection numbers on a number line to split the domain. And test a point in each interval to see if the second derivative is positive or the second derivative is negative. Okay, now why do we care about that? Is because concave up happens when the second derivative is positive. Because remember, you're positive, so you're happy. Concave down is when your second derivative is negative, so you're negative and you have a frown. Okay, so all of this step is from the second derivative. Okay, but you're basically doing the exact same thing over again, but with the second derivative. And if you get a change, I got this right down here, so change in f prime of x, that double prime of x, that's when you get a point of inflection or an inflection point. Okay, so if you change concavity, those are the points where you want to include in the graph. So you need to find their y values so you can plot them. Okay, so these are all the things that we want to include in our sketches.